Good evening. Welcome to the fifth problem solving session for the course Environmental Remediation of Contaminated Sites. So we have covered lectures and problem solving session till week 4. So for the first week, the content was about introduction about the various rules, especially focusing on the hazardous waste management, transboundary and movement rules 2016. And then we have seen hazard index and risk calculation for the non-carcinogens and carcinogenic compounds. And then we have moved to the treatment of contaminated groundwater and soils, in which we have seen the first treatment as pump and treat method. So in pump and treat method, we have seen that when the contaminant is present in more than one phase or it is associated with more than one phase, like it can be in dissolved phase or it can be sorbed on the soil and other components into the aquifer, and from there it can get re-released in the aqueous phase. So pump and treat is not suitable for such contaminants where we can see tailing and rebound. So, because we have seen there is a factor called retardation factor when the contaminant is participates between soil uh, and the aqueous phase. So, we have seen that there is increase in retardation factor, and when there is some non-aqueous phases inside the aquifer, then we have seen further increase in the retardation factor. So retardation factors tells us about how much more time will be required to remediate that site with pump and treat when the contaminants is present in more than one phase. So next we have seen the second method, which is the permeable reactive barrier. So PRBs are better as compared to pump and treat, because in PRBs, the structures above the ground are very limited. So we have very lesser number of monitoring wells are required, very less superstructure on the soil is required, so on above the ground is required. So that particular ground can be used for for purposes which was earlier it was being used. So in PRBs, all the we install the barrier layer into the aquifers, and the water pass through them and gets cleaned. And in the last week, we have seen few numericals based on design of the PRB, in which we were finding the thickness of the PRB layer. So the current week lectures, that is week 5, it is based on the case study which we were going through in previous week. That was the uranium contamination of a site in Utah. So the first 3 lectures for week 5 is based on this case study, and the last 2 lectures are on natural attenuation. So let's go quickly through this case study, because there are there are few questions in the previous years which is based on Utah case study. This graph was plotted for the various contaminants present in the groundwater, and this was done for uh, different time intervals, and we can see that uh, for various metals like aluminium, copper, iron, manganese, etc., this concentration into the groundwater is plotted. So here the site is shown like there was a stream flowing just beside the contaminated site, and from one end the stream was recharging the aquifer, and at the other end the water from the groundwater was recharging the surface water. So various monitoring wells were installed. So here we can see the concentration of uranium from the sediment desorption. So here we can see that In well number 3, maximum the concentration of uranium is maximum in soil and and also maximum into the aqueous phase. So three type of reactive media were used. So based on the lab studies, they have selected three medias. First was based on phosphate, where the mechanism was precipitation of the insoluble uranyl phosphate phase. So this uranyl phosphate precipitates out. So that like through this precipitation, uranium will be removed. Second was the zero valent ion, where reduction of uranium was taking place from +6 to +4 oxidation state, and subsequently precipitation was taking place. So here also the mechanism is precipitation. And in amorphous ferric oxyhydroxide, so this is the first phase chosen. So here the removal was by adsorption to the iron oxyhydroxide surfaces. So here the mechanism is sorption. So here the images is shown like from the same images we can see there, see these pores where where here these are the pores where sorption can take place. So here are some batch test result given for uh, uptake of the uranium on phosphate minerals, and here we can see that we are getting better graph for bone meal as compared to phosphate rocks and other. Again, breakthrough was plotted. So these studies were breakthrough studies of uranium were done in bore char column. And again, after breakthrough re-release study was done to see after we have exhausted uh, all the sites are available for precipitation and sorption of the uranium. So we the re-release study was seen that after exhaustion of the column, whether uranium will be released in the water or not. And then uranium concentration in different 3D batch tests were done using different media. So here we can see that these medias were giving very lesser uranium concentration, and these zeolite and these zirconia mixed valence pellets, it was giving very high concentration of uranium. So these are not good for removal of uranium. So we can select from these. So again, the concentration of the effluent after passing through the column was received, and here between AFO, that is amorphous ferric uh, oxyhydride and sand, and second is the zirconia foam zero valent ion palette sand was seen, and here we can see that in zero valent ion, the concentration in effluent is very less when very large amount volume of water is passed through the column, that is 6000 ml, that is 6 liters, more than 6 liter is passed, still the concentration in the effluent is less, that the column is not getting exhausted. But in AFO case, we were saying breakthrough that the concentration after this point starts to increase at very high rate. So So the various factors which consider in evaluating the materials to be used for making the PRV, first is the availability. The material should be available locally. It should not be very cost. It should have sufficient permeability. Eh, then surrounding aquifer material. If so, because if it will have a higher permeability, then water will pass through these PRBs, and if the permeability will be very less, then water will not pass through the PRB, rather it will pass through the sediments in vicinity of the PRB. Then there should be sufficient structural strength. Its crushing strength should be high enough, and then extent, rate, and duration of uranium removal is very important. Next is the mobility, that is the tendency for the material to move with the groundwater. Like materials like AFO, they can make mobile colloids, and these colloids can go in the groundwater. Next is the potential for re-release of uranium. It should be very, very high. If uranium is re-released in the surrounding water, then this PRB will is not good for removal of uranium. Next, the groundwater characteristics like possible detrimental effect on groundwater quality such as pH change or release of iron and phosphate. So, with because of use of some of the materials in the PRB, there can be changes in the pH and other minerals constituent in the groundwater, and these should be minimal. So now let's move to lecture number 22. So we have seen all the factors. So from the batch and column uptake study, it was seen that bone meal and bone charcoal appetite would be more effective on per gram basis in removing dissolved uranium. Sorry. So that's why finally three compounds was chosen. First was AFO mixed with some gravel, and next was zircona zero valent iron foam pellets, and the third was CP3 pellets. So all these three were placed into the contaminated site. So first was the amorphous ferric hydroxide, second was zero valent iron, and this black one is the bone jar phosphate. So these three PRBs were installed. So this is the top view. So this is our PRB. So inside the PRB, there were some monitoring wells, and before that also there is some monitoring wells, and after the PRB layer is also monitoring wells. So let's move. So this is the monitoring well setup. So here we can see that there is a lot of containers. So here are on-site monitoring where all the contaminants and also the pH and other are measured on the site itself. So these are the characteristics of. So finally the results. So the percentage removal of uranium in phosphate and AFO PRBs exceed 70% for most measurements, and zero valent iron PRB has lowered the input for uranium concentration by more than 99.9%. So better removal was in zero valent iron PRB. So here's a graph is shown for the concentration of uranium in milligrams per liter for different rows of PRB layers. So here from the graph we can see as the distance in the PRB is increasing, concentration is decreasing because these uranium contaminants will be sorbed or precipitated out, and as the water will come out from the part PRB, the concentration of the contaminant will be very, very less. So these are for the zero valent ion that here we can we are getting the concentration reduction in concentration, and pretty much it is same. So the concentration of uranium is getting reduced very faster in zero valent ion as compared to the other PRBs. So here graph is shown for the removal of uranium by different PRB layers. So here we can see that in zero valent ion or more than 99% or nearly more than 99.9% of the uranium was removed. But in phosphate and AFO, the removal was not that good. Okay, let's see how the pH changes. So here we can see that the pH in case of AFO barriers is high, where sorry, zero valent ion barriers is high, whether on and in the AFO barriers the pH are fluctuating, but on these ones, that is phosphate barriers, the pH is lesser as compared to zero valent ion and AFO PRPs. So what happens in zero valent ion, that this is the entire oxidation reduction reaction which is being given, that iron gets oxidized to Fe2 plus, and it gives electron, and if oxygen will be present in the system, then it will take the electrons and it will get uh, reduced, and finally OH minus will be released. So since hydroxide ion is getting released, that's why the pH of the water will increase. That's why we are seeing increase in pH of groundwater in case of zero valent ion. Also here the change in concentration is given. So here we have seen that in previous graph, that in zero valent ion the redox reaction is taking place with reduction of oxygen. That's why the concentration of the oxygen has reduced in case of zero valent ion. That's for the concentration of ferrous ion. So for zero valent PRP, we can see that the concentration initially is high, so and then the final concentration decreases. So uh, yeah, so this can be because when the water with uranium passes through the PRB initially, the reaction rate will be very high. So if iron Fe is zero, that is zero valent ion will oxidize to give electrons. So that's why initially the concentration of Fe2 plus will be very large, and slowly as we move forward, the concentration will decrease. So these two indicates the monitoring wells which were on the different line, and ZVIR1, these one shows the monitoring line in one line, and these two shows the monitoring line in the monitoring belts in the other line. So this one is for the first, and ZV2, this shows the monitoring wells here. So that's why we are seeing different grams. So this is for the left one, and this is for the right side of the monitoring well. So here we can see that the concentration of Fe2 plus is higher in the right side. So maybe it can be due to the presence of a more material here, or maybe due to the more water flowing through this, or more contaminants passing through these lines. So in AFO, the removal is through precipitation. Here is no role of ferrous ion. That's why the concentration here is very less. So let's move to the lecture 23rd. I think this is the last for the Urta case study. So this graph shows the oxidation reduction potential. So higher will be the oxidation reduction potential. So if the oxidation potential will be very high, then that compound will oxidize very faster. So this table shows the overall cost and duration of the project planning. So let's finally go to the conclusion. So it was seen that PRB is an efficient and financially viable means of remediating the uranium contaminated groundwater, and it can also attenuate other contaminants. And the results of this project shows that it has wide applicability. But for installing PRV, we should know proper knowledge about the groundwater flow is very important throughout the year, because with the change in the season, like in rainy season, the groundwater flow can change. So all the data for all these changes in the groundwater flow is very important for success of the PRVs for removal of contaminants. Now let's move to the lecture 24. I think from here there is a natural attenuation. So natural attenuation, it can be non-destructive or it can be destructive. So in non-destructive, concentration of the contaminants reduces. It changes form from one form to the other form, but it is not getting uh, deteriorated or decomposed. So the mechanism here can be sorption, that is adsorption or absorption. Here can be dispersion or diffusion due to concentration difference. There can be dilution or there can be volatilization. If the compound is volatile in nature, then it will partition between the gaseous form and the dissolved form or the aqueous phase. So all these are the non-destructive attenuation mechanism. So there can be destructive attenuation where the mass and concentration of the contaminants decreases. So these destructive attenuation, the ones such as the biodegradation, and in biodegradation can be aerobic or anaerobic. So aerobic biodegradation is mainly used for the petroleum hydrocarbon. So these hydrocarbons are very good electron donors. So they very easily get oxidized. And these electron which are donated by them, that can be taken by electron acceptors like oxygen and nitrate. And microorganisms, in presence of these electron acceptors and donors, they can thrive and they can grow and slowly remove these hydrocarbons. So there can be anaerobic, because if the so for hydrocarbons they are in the reduced form, they can get oxidized easily. So that's why we need aerobic conditions, because oxygen is a very good electron acceptors, and microbes prefer oxygen over other electron acceptors because the energy produced by taking oxygen as an electron acceptor is very high as compared to the other electron acceptors. So if we have some chlorinated solvents, so they are already in their oxidized form, so they need to be reduced. So here they will accept the electrons. So that's why here we need anaerobic conditions for the removal of these contaminants. Also during the remediation, there can be both abiotic and biotic degradation. So biotic degradation will take place because of the microbes, and abiotic degradation can take place due to processes like hydrolysis, dechlorination, and others. And abiotic and biotic degradation, these also goes simultaneously in the system. So there are various naturally occurring bioremediation. If suppose microbes are, and it is evident that microbes are present everywhere. So if the microbe is present in the groundwater also, then because of the metabolic activity of the microbes, some of the contaminants can be removed from the groundwater. So So there is natural degradation which takes place in the groundwater, but there is one thing which is very important is kinetics. That whether that removal of the contaminant will take place in a few minutes or hours, or it will take years or hundreds of years. So the degradation can be incomplete. Also, in during natural remediation, it can happen that the contaminant is converted from less toxic form to more toxic form. So that's why we need to have a check on that. And biosimulant, in which some oxidizing or reducing agents are added in the system, and they fasten the degradation process. So here we can see the example that's this aquifer is contaminated with hydrocarbons, and that's why air is purged inside the aquifer to give oxygen, and the microbes present in this contaminant can take the oxygen, and they can produce energy, and they can multiply, and, and very fastly they can degrade the hydrocarbons. And also here we can see there are airflow, because the hydrocarbons are something which can partition between gaseous and liquid phase. So air is also taken out from all these gaseous contaminants are taken out from the aquifer, and they are treated separately. So in biostimulant, we add some oxidant or reductant to increase the bioavailability within the medium. So here the example is given for air. Next is bioaugmentation, where some microbial strains are added which can easily break down the contaminant. Suppose one example is given for activated sludge process. So activated sludge process, or ASP, is used for the secondary treatment of the municipal sewage. So it is a biological process where the microbes, in presence of oxygen, convert the organic matter into CO2, and here the microbes release enzymes which act as a catalyst in fastening the process. So the and ASP is very widely used process for secondary treatment of the sewage. So like this, we can add some microbes in the aquifer system, or some strain of microbes which are known to degrade a particular contaminant at a much faster rate. So we can introduce these microbes, and they can easily break down the contaminants. So let's see some of the advantages and disadvantages of natural attenuation. So if we see the advantages, then the cost requirement is very less, because we are adding either microbes, or we are adding some biosimilars. So we are not adding making any structure, large structure like pump and treat method here. So the overall cost will be very less, or either a small part or the entire site can be remediated by using this method. And it can also work with other methods. Suppose we have some PRBs also, and we can also add the microbes inside the our system to degrade the to degrade the contaminants. And one more advantage here is that we are not just changing the form of the contaminant. From, like in uranium, we are reducing it from +6 to +2, or we are either precipitating it. So we were not destroying the uranium contaminant. We were just changing its form from one form to the other. But in natural attenuation, proper degradation of the contaminants will take place, because microbes will take these contaminants, and they will decompose these or degrade these. So proper degradation of contaminants takes place. And here no above structure surface structure is required, so the ground can be used for various purposes. But the disadvantage here is kinetics. So the rate of degradation by the microbes can be very less, and also incomplete degradation can take place, which may result in formation of more toxic form of the contaminant. And here long-term monitoring will be required, because if we are adding some uh, different state of microbes which was not usual to that aquifer, then we need to monitor into about the changes which will take place inside the aquifer. Here we need to do extensive site characterization, and here also the site conditions can change, and also there can be chances that the site is not suitable for natural attenuation. So these were the disadvantages. So here example is shown, like in aerobic process, there will be some electron donor. Suppose the donor is a hydrocarbon, and there will be some electron accepted. This can be oxygen. So the end product will be CO2, water, and energy. And this energy, microbes will now use to grow and multiply. And when oxygen will not be present, then the other electron acceptors are given like nitrate or nitride, Fe3 plus, sulfate, CO2, or chlorinated hydrocarbons. So here we can see that in this table, chlorinated hydrocarbons are at the bottom, so they will so out if all above electron acceptors are present, then RCl will not be taking part into the oxidation reduction reaction. That's why if we want RCl to be removed, then these other electron acceptors should be removed from the system. Then only the microbes will prefer chlorinated compounds as electron. Then only RCl will be preferred over other electron acceptors. So, like this way, we can remove the contaminants. So, suppose we have a system where we have hydrocarbons and we have PC. So, we can remove both if we do not have any other electron acceptor. If oxygen would have been present, then hydrocarbons would have been removed because oxygen will accept the electrons given by hydrocarbons. But if we want PCE2 or TCE to be removed, so what we need to do is like we need to remove all the electron acceptors present in the system. Then only then these chlorinated compounds will accept electrons and they will get reduced. Sorry. So this is all for the natural attenuation. So natural attenuation is being carried to the next week lecture. So we will see some numericals based on remediation by microbes, and also we will see some theory about this. So but till now the week 5 was about the case study of Kuta, yeah, which was contaminated by uranium, and then last two lectures were natural attenuation, where we can see that it can be both that removal of contaminants can be done by both constructive and destructive methods, and in microbes these are mainly destructive method. And because contaminant is completely converted into a different form, or it is completely degraded. And then we have seen what are the advantages and disadvantages, what is biosimilants, and what is bioaugmentation. So now let's uh, go to the question part. So I hope my slides are visible. So it is a biological process where the microbes. Give me a minute. Okay, my screen is visible. So let's move to the first question. So the question is, which of the following statements is or are true? First, in destructive attenuation, the mass of the contaminant decreases, leading to a decrease in the relevant concentration. Next, in non-destructive attenuation, the concentration of the contaminant decreases and the mass of the relevant compound in the entire system increases. Option C is in destructive attenuation, the mass of the contaminant increases but the relevant concentration decreases. And the last option is in non-destructive attenuation, the concentration of the contaminant decreases while the mass of the relevant compound in the entire system remains constant. So we have to select the correct statement for destructive attenuation and the non-destructive attenuation. So there can be more than one option which will be correct. So I'll give you all 3 minutes. Just take your time and write the option which you think is correct in the chat box, and then we will discuss. So let's see which of the following are the correct option. So the first option, that in destructive attenuation, the mass of the contaminant decreases, leading to a decrease in the relevant concentration. So this statement is correct. That in destructive attenuation, the overall mass of the contaminant decreases, and because of decrease of the mass of the contaminant, it leads to decrease in the concentration. So next option is, so in non-destructive attenuation, the concentration of the contaminant decreases and the mass of the relevant compound in the entire system increases. So this is not correct. Option C is, in destructive attenuation, the mass of the contaminant increases but the relevant concentration decreases. So this is also not correct, because we have seen in destructive attenuation, mass of the contaminant decreases, and because of that there is relevant decrease in the concentration. Sorry. So the last option is, in non-destructive attenuation, the concentration of the contaminant decreases while the mass of the relevant compound in the entire system remains constant. So this option, the D option, is correct for non-destructive attenuation, is that the contaminant is converting from one form to the other form, but the overall mass of the compound in the system remains constant. So since it is converting from, suppose, from the more aqueous phase, the contaminant can convert to can precipitates out. So that's why the concentration of the contaminant in aqueous phase will decrease, but overall mass of the contaminant in the system will be same. Question is, select the correct answer regarding the removal mechanism for zero valent iron pellets or sands. So this question is based on the UTA case study. We have to find out the removal mechanism for zero valent iron for the uranium. So first is adsorption, B is diffusion, C is reduction and then precipitation, or D precipitation. So I'll give you 3 minutes. Just take your time and write the option in the chat box, and then we'll
Yes,
discuss.
correct.
So the correct option for question number 3 is reduction and then precipitation. So the mechanism for removal of uranium was like it was getting reduced from +6 to +4 and then was getting precipitate out. So now let's move to question number 4. So the question is, which of the following factors are considered while choosing a relevant PRB material? So first is effect of groundwater quality, next is mobility, C is permeability, D is resistance to compactive crushing when placed in ground. So we have to select the factors which are important while choosing a relevant PRV material. So there can be more than one option which can be correct. So please write the option which you think is correct in the chat box and then we'll discuss. So for the factors given are first effect of groundwater quality. So this is important. We need to consider the first uh, groundwater quality before choosing any PRB material. So A is correct. So next is monitoring. Sorry. So next is mobility. So it is also important to consider the mobility of the material. So the PRB material should not form colloids and it should not go in the groundwater. So mobility is one. So mobility should be less. Next is permeability. So the PRB material should be highly permeable, or it should have more permeability than the surrounding sediments. Because if the water needs to be passed through the PRB layer, so permeability of PRB is also important. And the last option, that is resistance to compactive crushing when placed in ground. So this is also important, that the PRB material
More
should.
permeable, more permeable than the aquifer.
So are you saying something? So the PRB material should have some crushing strength, because we have to place that material inside the ground. So it should have some resistance to compactive crushing when placed in the ground. So A, B, and C, all these four options are correct. That we need to consider all the following four options while choosing any material for installing in PRB. So let's move to the next question.
It, C, so D is also correct, right?
Yeah, D is also correct.
D is also correct.
Yes, A, B, C, and D, all four are correct.
Four.
Let's move to the next question. So the question is, select the correct advantages of natural attenuation as a method for remediation. So we have to select the options which has advantages of the natural attenuation. So first is high cost. B is monitoring is not required. C can be used in conjunction with other remediation techniques. Or D can be applicable to whole or a portion of the contaminated site. So again, I will give you 3 minutes. Just take your time and write the option in the chat box, and then we will discuss. Let's see which of the following options are correct. So first is high cost. So this is not correct because natural attenuation process requires very less cost as compared to other methods for remediation. Next is monitoring is not required. No, monitoring is required for natural attenuation remediation also. So B is also not correct. C can be used in conjunction with other remediation techniques. So this is correct that we can use it with other remediation techniques like PRB. And the last option is can be applicable to whole or a portion of the contaminated site. So this is also correct that we can use natural remediation for the entire site or to a part of the site. So C and D are the correct answer. Now let's move to the next question. So the question is in destructive natural attenuation, total mass of contaminant decreases in the system. So this statement is given for destructive natural attenuation and we have to say whether it is true or false. So please write the option in the chat box and then we will discuss.
True. True. Contaminant decrease.
So yes, the statement is correct that in natural attenuation, total mass of the contaminant decreases in the system. So yeah, that's why the concentration of the contaminant decreases. So A is the correct answer that this statement is true. So now let's move to the next question. So the question is in Utah case study, the decrease in uranium concentration using AFO that is amorphous ferric oxyhydride PRB treatment is due to A precipitation, B dilution, C adsorption or D precipitation and reduction. So in Utah uranium concentration, in Utah case study with uranium contaminant, three PRB materials were used. First was AFO, then zero valent iron, and one was bone meal. So we have to select the mechanism which was taking place for uranium removal in AFO PRB. So I will give you 2 minutes. Just take your time, write the option in the chat box, and then we will discuss. So the mechanism for removal of uranium using AFO was adsorption. So uranium was getting adsorbed on AFO layer. So here the mechanism for uranium removal was adsorption. Now let's move to question number 8. So the question is, the permeable reactive barrier material should have dash porosity compared to the porosity of the surrounding aquifer material. So the options are A higher, B lower, C equal, or D none of the above. So we have to select the correct option. So I will give you 2 minutes. Just take your time and write the chat option in the chat box. So the PRB material should have higher porosity as compared to the porosity of the surrounding aquifers for the groundwater to flow through the PRB material. If the porosity will be low, then water will not flow to the PRB material, rather it will flow to the surrounding sediments. So that's why the porosity of the PRB material should be higher as compared to the surrounding aquifer material. So let's move to the next question. So the question is, select the correct statements regarding the conclusions in UTA case study related to PRV selection. So the first statement is, PRVs are efficient but financially not viable means for remediating uranium contaminated groundwater. Option B is they help attenuate other contaminants by means of reduction. C, the result of this case study have wide applicability. And the last option is the PRB can be used in remediating contaminated groundwater sites with contaminants other than uranium. So four statements are given based on the UTA case study, and we have to select which of the out of four are correct. So I'll give you 2 minutes. Just take your time and write the option in the chat box, and then we will discuss. So the first statement that PRB are efficient but financially not viable means for remediating uranium contaminated groundwater. So this statement is not correct. We have seen that the overall cost for treatment for this Uta site was not very high. So PRBs are efficient and also they are cost effective also. So A is not the correct option. Next is they help attenuate other contaminants by means of reduction. So this option is also correct that other contaminants can be also removed by reduction. Next is the result of this case study have wide applicability. So the statement is also correct. The third option is the PRB can be used in remediating contaminated groundwater sites with contaminants other than uranium. So this is also correct that we can use permeable reactive barriers for remediating groundwater sites contaminated with contaminants as well. So B, C, and D are the correct options. So B, C, and D, we have C. So C is the correct answer. Okay, now let's move to the next question. So the question is in context of competing electronic receptors, choose the accurate sequence indicating the microbe's preferred order of electronic receptors. So we have to arrange the given, we have to select the correct option out of these four, in which the sequence for acceptance of these electron acceptors by the microbes is preferred. So again, I'll give you 2 minutes. Just take your time, type the option in the chat box, and then we will discuss.
CL, CL is what? This RCL, madam.
Yeah.
RCL is what?
R shows alkyl groups, hydrocarbons with chlorine.
Okay, hydrocarbon.
So, out of all the electronic acceptors, oxygen is preferred first, followed by nitrate, and then sulfate, and lastly, chlorinated hydrocarbons. So, because this is a sequence, because when oxygen is the electron acceptors, then with redox reaction, highest amount of energy is produced, which will be used by microbes to grow and multiply. So followed by nitrate, nitrate will produce lesser energy as compared to oxygen, and then sulfate will produce uh, lesser as compared to nitrate, and the least energy will be produced by RCl when it will be the electron acceptors. So B is the correct answer. So these were the questions based on week 5 material. So I have added I think two more numericals based on the PRB. So let's try to solve those. So let's try to solve first this numerical. So the question is, a contaminated groundwater plume with a concentration of 10 milligram per liter of
11.
trichlor. Yes, yes.
Saying that question number 11 is also there, na? But we will
No,
look
first
first.
we will solve 12 and then we will go to 11. So there were 10 questions based on week 5. Now I have added these numericals from my end. So we will try to
Okay, fine.
solve these.
And question number 2 is also not done. So will be done or not?
We can do the question number 2 in the next week. I will add that question.
Understood. Okay, okay, thanks.
The question is, a contaminated groundwater plume with a concentration of 10 milligram per liter of TCE
Okay, fine, understood.
is flowing through a permeable reactive barrier made of zero valent iron with a length of 20 meters, a width of 5 meters, and a porosity of 0.3. The residence time of TC in the PRB is given as 300 days. The reaction rate constant for TC degradation by zero valent ion is 0.05 per day. We have to calculate the contaminant concentration leaving the PRB, assuming a plug flow model and neglecting a dispersion effect. So we have been given initial concentration, we have been given rate constant, yes, reaction rate constant is given, and the residence time is also given. So we have to find out the final concentration of the contaminant by assuming plug flow model. So we have seen in week 4 lectures by using assuming plug flow models, following formula was derived, that concentration at any time t is equals to C naught e to the power minus k theta. So where k is the reaction rate constant, theta is the residence time, C naught is the initial concentration, and Ct is the concentration at any time t. So we have been given C naught, K and theta, and we have to calculate Ct. So I will give you 2 minutes. Just please do this calculation and write the value which we are getting in the chat box. Let's see how to solve this question. So so we have the initial concentration as 10 milligrams per liter. And we have been given the residence time of 300 days. And reaction rate constant is given as 0.05 per day. So we do not need to convert the residence time into hours because K is given in per day only. So using the above formula, concentration or final concentration will be C naught is 10 e to the power minus K, that is minus 0.05 into 300. So on solving this, we will get the I think it's coming out to be 0.045.
Point
Do not have my calculator,
minus
so just give me.
or minus 50.
We are getting it as, yeah, your answer is correct. 3.059 into 10 raised power 10 raised power minus 6 milligrams per liter. So this is the final concentration of now TC in the TC in the PRP after coming out from the PRP. So now let's move to the previous question. So this is the question that we have. A plume is to be remediated by PRB is 200-meter wide, 20-meter deep, and 20-meter wide and 10-meter deep. We have aquifer porosity is 0.35 and reaction rate constant in the PRB is 0.28 per hour. TC maximum concentration is 10 milligrams per liter and the target concentration is 2.5 micrograms per liter. And we have concentration of zero valent ion in batch reactor is 125 grams per liter. The PRB will be designed with a mixture of zero valent ion and sand, and the porosity of mixture is 0.35 and its bulk density is 2.7 kg per liter. We have Darcy's velocity through PRB is 20 meter per year, and consider the system behaves as a pseudo first order with a reaction rate constant of 0.8 per hour. Calculate the minimum thickness and mass of iron required for a funnel and gate PRB, in which the gate is 10 meter of the width of the plume. Assume that the depth of the gate portion is same as the depth of the plume. So we have solved previous similar question in the last week problem solving session where we were having a continuous PRB. So this question is extension of that this is not a constant continuous PRB, rather it is a funnel and gate PRB, and the gate is of the PRB is 10% of the width of the plume. So let me give you a hint to solve this question. So to proceed with this question, first we have to find out the retention time. I think the initial concentration on the final concentration is given. So let me show what is given. We have given C naught as 10 milligrams per liter. We will convert into micrograms. So 10,000 micrograms per liter. We have final concentration as 2.5 microgram per liter. We have given reaction rate constant of 0.28 per hour. So using this, we can find out the retention time. So first find out the retention time. So we have to assume as a pseudo first order reaction rate. So for pseudo first order, concentration at any time is given as C naught e raised to power minus k theta. So on putting everything, we can find out what will be the reaction retention time of the contaminant in the PRP. And after the retention time, Darcy's velocity is, I think, given. Yes, Darcy's velocity is given. So Darcy's velocity is given by the formula flow rate in per unit cross-sectional area. So from there, we can find out the flow rate, and with the equation for a relation between retention time and porosity and flow through the PRB, we can find out the thickness of the PRB. So let's find out the retention time. So we have CT as 2.5 equals to C naught is 10,000 milligrams. E raised to power minus k is 0.28 into theta. So on solving this, we are getting retention time as 29.6 hour. So we have solved this question of finding the retention time in week 4 also. Now we will find out the discharge. So we have been given the Darcy's velocity is 20 meter per year. And Darcy's velocity is given as discharge through that cross-sectional area, discharge per unit cross-sectional area. So we can easily find out discharge by multiplying Darcy's velocity, that is 20 meter per year, with the cross-sectional area, that will be 20 by I think 10 meter is the depth. So we will convert it into hours. So 365 days multiplied by 24. So on solving this, we will get Q. So on solving this, we are getting value of 0.45, I think it was. It's coming out to be 0.457 meter cube per hour. Now we know that the retention time is given by porosity of PRB times volume of PRB divided by discharge passing through that PRB. So we can write in terms of porosity of PRB, volume we can write in terms of uh, width of PRB into depth of the PRB into thickness divided by discharge. So we have to find out the thickness. So thickness will be given as Q into theta upon porosity of PRB into width into depth. So retention time we have calculated it as 29.6. Discharge we have calculated as 0.457. Porosity of PRB is I think zero point 0.3. Porosity of the PRB is 0.35. So width of the PRB is uh, gate of the PRB is 10% of the width of the plume. So it will be 10% of the width. So 10% of the 20 will be 2 multiplied by uh, depth of the PRB. So depth will be same. You have to assume that the depth of the gate is proportion to is same is proportion is same as the depth of the plume. So depth here will be 10. So on solving this, we will get the thickness of the PRB. So it's coming out to be 1.932 meters. So this much is the thickness of the PRB required. Now we have to calculate the mass of iron required for this PRP. So, so mass of iron required is given as porosity of the PRP. Sorry, first fraction of iron in the PRB. So fraction of iron multiplied by bulk density of the PRB material into volume of the PRB. So we have been given around 30% by mass is iron, so it will be 0.3. Density is 2.7 kg per liter. So to convert into kg per meter cube, if we will multiply it with 1000, so it will be 2700 kg per meter cube multiplied by volume of the PRB. So we have width as 2 meters, depth as 10 meter, and thickness we have calculated as 1.32 meters. So this will give us the overall mass of iron required. So it's coming out to be 31,298.4 kg. So meter cube, this meter cube and the meter cube from the volume will cancel out, and we will get the mass of iron required in kg. So I hope the solution is clear. So if you have any doubt, you can ask, or else we can move to the last question. So this question is based on the retardation factor which we have calculated in the pump and treat method. So the question is a soil with a porosity of 0.3, bulk density of 1.5 gram per centimeter cube and a partition coefficient of 100 milliliters per gram is contaminated with a chemical. Determine how much slower this contaminant will move through the aquifer compared to the groundwater itself. So in pump and treat method, we have calculated retardation factor when we have a contaminant which gets sorbed onto the sediments and also is in equilibrium with the aqueous phase. We have calculated the retardation factor for this condition, and also we have calculated the retardation factor when there is some non-aqueous phase liquid in the aquifer, which further increases the time for the treatment of the groundwater with pump and treat. So let me give you the formula for the retardation factor. Retardation factor in this case will be given as 1 plus KD, that is the partition coefficient multiplied by bulk density of the contaminant, sorry, bulk density of the sediment or the soil divided by the porosity. So we have everything is given. We have porosity as zero point 0.3. We have the bulk density of the soil as 1.5 gram per centimeter cube. And we have the partitioning coefficient Kd as 100 ml per gram. So everything is given. We just have to put in the formula. So while putting these values, we have to see the units in which these terms are given. So after putting it, we can find out the retardation factor. So please do the calculation and write the value which you are getting. So 51 is not the correct answer. So let's find out the retardation factor. So it will be 1 plus Kd is given as 100 ml per gram, and we have porosity as 1.5 gram per centimeter cube. So we do not need to do any conversion because 1 ml is equivalent to 1 centimeter cube divided by porosity, that is 0.3. So on solving this, we are getting 1 plus 500. So retardation factor is 501. So these were the questions. So these were the questions based on week 5 and some questions based on previous week material. So I hope all the questions were clear to you all. So if you have any doubt, then you can ask or we can end the session here. So if there is no doubt, then okay, thank you so much for joining. Have a nice day. We will meet on next Sunday from 6 to 8 p.m. Thank you.